So, hello everyone. Today we are going to start the second lecture of this week. So, this is a continuation of downstream processing. So, in the last lecture we discussed about the adsorption separation process, and today we will be discussing about membrane separation. So, in the last lecture we discussed what is the adsorption. It is a surface phenomena and type of adsorbent, particularly based on its origin. It may be the some inorganic material, it may be some bio based, or it may be some polymeric materials. Then we quickly discuss how to differentiate between adsorption and absorption. Then followed by that, once adsorption is taking place, then we need to see with time adsorption varies and adsorption capacity also vary with the concentration. So, that those data we consider as adsorption isotherm, and we discuss a few adsorption isotherm like Pandey and Langmuir adsorption isotherm, and further depending on the nature of interaction between surface and your adsorbate or the molecule, it may be the van der Waals interaction, then it is called physiosorption. So, they are the having the weak interaction. So, they are easily to have the reversible adsorption cycle, but when it is chemi-adsorption means there is a formation of some chemical bond. So, they are slightly difficult to reuse and regenerate because of the strong intermolecular interactions. So, typically if you remember, so we go like first we have to load your adsorbate on the surface, then you have to go for washing, then you have to go for elution, rather you can say removal of your adsorbate, then further washing, and the next step is the regeneration, where you have to regenerate in order to reuse the adsorbent for multiple number of cycles. So, today we are going to discuss the basic of membrane filtration, then what are different types of membrane, what should be its properties, then what is the theory of membrane filtration, what is the driving force, what is the resistance, and then we will see what are different type of membrane filtration setups. So, membrane filtration, they are also part of downstream processing we are discussing. So, if you remember, we discussed the filtration in the very first step of downstream processing, that is used for the solid liquid separation, or particularly for the first step, that is the separation of cells and others solid impurities. So, there we discuss the conventional filters. So, basically it was press and frame filter and rotary drum filter. But here we are going to discuss more about the membrane filter, and separation is based on the specific pore size. So, they are used in the latter part of downstream processing for the separation, concentration and purification. So, in this lecture we will be mostly focusing on this concentration and this purification part. Application, as I told, it is used to for the removal of cells and debris, concentration of proteins, removal of viruses, recovery of precipitates, solvent clarification and buffer exchange. So, how does it work? So, basically it is a pressure driven fluid flow. So, delta P is a driving force to separate the components. What is the theory? The theory says the pressure drop exerted across the porous polymer membrane causes the smaller particle to permeate through the membrane. So, the smaller particle will pass through the membrane and larger one will be retained. In this way you separate based on the size. However, it is not very selective because it is just based on the size. So, can cause co-retention of various substance with similar property, particularly the similar size. Major application, it is used for the concentration of final product, because once you pass through the membrane, so most of the part can be considered either reject or permeate, and in this way the volume ratio vary quite significantly. So automatically that your desired product get concentrated. So advantage, it is a low energy intensive process. You can operate under aseptic conditions and there is no exposure of harsh chemicals. Disadvantage, so this robustness and reliability of the membrane, that is a major concern to have the membrane. In addition, there is a challenge of fouling and resistance to our cleaning chemicals. Further, we require solvent and wide pH ranges. It may be for the cleaning, it may be for the adsorption, desorption, or even it may be for the washing of membrane. So, you just see this is a typical schematic of membrane separation, where you are pumping the feed and it has some inlet pressure and it is also having the outlet pressure. So, the smaller size, the particle whose size is below the membrane cutoff will pass through it, that we are calling as a permeate. And the remainder which is retained, they are called the retenate or reject. So, this is retenate. So, we are measuring pressure at 3 point, pressure at inlet, pressure at outlet for the retenate and pressure for the permeate. Now, if you know total feed now is distributed into two parts, you say this is R and this is P equals to R plus P. Now, based on that we can define the retention coefficient, and retention coefficient is defined as R as concentration in the reject minus concentration in the permeate divided by concentration in the reject. So, it becomes 1 minus Cp upon Cr. So, this shared selectivity of membrane with respect to a solute is quantified using rejection or retention coefficient. So, it says how much concentration is retained here and how much concentration is there in the permeate. So, you can see this is a cross flow membrane. So, what we discussed in the last slide, this is a cross flow setup where the feed is passing through it and it will cross through the permeate, only will pass through the membrane under pressure. So, this is the direction of feed and direction of retenate, but there is a conventional filter where the feed is passed across the membrane. In this case, typically there is a deposition of filter cake on the membrane. So, in the case of conventional filter, we mostly go with this cross flow pattern where the filter cloth is there and feed process passes through it and there is a deposition of filter cake. While in the case of cross flow, it minimizes the cake formation, but still we will see the challenges with the membrane resistance is still exists. So, what should be the ideal membrane property? It should have well defined particle or solute rejection characteristics. It should have very well defined particle size. Further, as we are going to operate under different temperature, pH and operating pressure, so it should be resistance to those variations. Further, it should allow the high rate of filtration. It should have good mechanical property, and last is very important, the cost of membrane. So, it says easy and economic production. So, there are various materials, mostly the polymeric source origin like polysulfonate, polyether sulfonate, polyamide, polyvinyl chloride, cellulose acetate and ceramics. So, these are the materials which are being used for the preparation of membrane. So, mostly there are polymers and there are few ceramic membranes are also there. And if you just see, these are different polymers, so they may also have the different functional groups as well. So, depending on the functional group, again they help in different kind of separation process. Now, there are two main category of membrane structure. One says it is a symmetric or homogeneous, other is asymmetric or anisotropic. So, in the case of symmetric membrane, they have the uniform pore size throughout the depth of the membrane. So, it offers the selective barrier to the passage of particles. So, in this case, the filtration can happen in the both the direction, and further the efficiency drops with the increase in the clogging of the pores inside the membrane. So, it acts both as the depth as well as the surface filters. While in the case of asymmetric membrane, it has a thin skin, typically 0.1 to 1 micrometer layer with very small pore, and that is supported by the microporous support. So, in this case it is very important now your feed should pass through the skin layer. So, the upper skin layer retains the particles, and microporous supports it allows the fast flow due to high permeability, and diameter of pore varies throughout the membrane's depth. So, because of this arrangement, the direction of filtration is one direction from skin to the microporous layer, and it mainly acts as a screen filter. And so, here as the screen is able to retain your particles, so they are less blockage and they are easy to clean as compared to the symmetric membranes. Now, we will go through the theory of membrane filtration. So, the aim of this topic is to calculate how much membrane area is needed, because area is one of the design parameter for the membrane, and it decides the number of filtration units required for the desired output and time taken to filter a set volume. So, typically we will talk in terms of permeate flux. It is defined as Fp upon A. It means permeate flow rate divided by membrane area. So, it will have unit of meter cube per meter square into per second. J is Fp upon A. So, permeate flux is defined as permeate flow rate divided by the membrane area. Now, it says the driving force is delta P. So, you can calculate P delta P as P pressure at the feed point minus pressure at the permeate point, feed side and the pressure at the permeate side. Now, further in some cases there will be osmotic pressure of the solution on either side of the membrane. So, we can incorporate the osmotic pressure part as well. So, it becomes delta P now as Pf minus Pp minus osmotic pressure part, osmotic pressure feed side minus osmotic pressure on the permeate side. And how we calculate the osmotic pressure? Pi is equal to I CRT. I is the number of ions. Let us say if it is CaCl2, that I is 3. If it is NaCl, then I equals to 2. C is the total molar concentration of solute, R is the gas constant, T is the temperature. So, in this way you can calculate this osmotic pressure using Van 't Hoff equations. So, we have calculated delta P, and that is the driving force here. Now, many times this when you are calculating the Pf, So, what we see, the permeate pressure is mostly constant during the filtration, but pressure at the membrane surface may differ between inlet and outlet due to pressure drop. So, typically what we do in that case Pf we are replacing with the average of Pi plus Po upon 2, or you can say Pf plus Pr upon 2. If you remember the slide here we discussed, so there will be Pi, Po and Pp. So, now what we are saying, Pf will be Pi plus Po upon 2, we are taking the average of these two, and permeate pressure is typically remains unchanged. Further what happens, there is one term called concentration polarization. So, once you are passing a liquid through the membrane, let us say you are passing the clean water through microporous membrane. So, it says the J should be directly proportional to delta P. It says J is directly proportional to delta P dP square epsilon divided by 32 x into mu P. So, this is a Hazen-Poiseuille equation which relate the flux with delta P transmembrane pressure, diameter of the pores, surface porosity, pore depth and the viscosity of permeating liquid. So, according to this the flux should be linearly related with delta P. But if you see this slide here, so for the pure solvent it is following the Hazen-Poiseuille equation, but when you are having certain biomacromolecules which need to be separated, let us say for example protein 0.65%, 0.39, 0.65%, 3.9%, 6.5% protein. So, what we are seeing is initially it is having linearity and further it is getting saturated. It means there is a deviation from this linear behavior between J and delta P. So, this phenomena is known as this concentration polarization. So, basically what we are saying that at the membrane there is a deposition of a permeate, for example here the protein molecule. So, it gets deposited, and once it is deposited it is causing the concentration polarization. So, ideally this concentration permeate flux it should be directly proportional to the transmembrane pressure for pure solvent. But when we are having the fluid with cells or protein, the flux only increases with pressure at a low value, and at higher value it levels off, and this nonlinear flux arises from the concentration polarization, or you can see the solutes are getting kind of deposited near the membrane. So, this reduces the membrane performance and lowers the permeate flux. You can just see it is lowering the permeate flux. So, apart from this there is another model, it says you can consider the flux proportional to driving force delta P and divided by resistance RT. Now, it says there will be two resistance, RT will be equals to the membrane resistance plus RC is the coming from the concentration polarization. Now, how to get the value of Rm? If you can remove the value of Rc, how to remove the value of Rc? If you pass through the pure solvent, let us say water. If you are passing through the pure solvent, in that case this Rm will be delta P upon J of the pure liquid, let us say water. So, in this way we calculate the this intrinsic membrane resistance. However, to calculate the value of Rc or resistance due to concentration polarization, so it says there are different factors which regulate the Rc value. It is under transmembrane pressure, cross flow velocity, fluid viscosity, temperature and the solute concentration. But across all these it says RC and pressure, they are directly proportional quantities. RC and cross flow velocity, they are inversely proportional to each other, and value of, as I have discussed, this value of Rm, it is independent of pressure and cross flow velocity, while this RC value, it depends on the cross flow velocity as well as the pressure. At low value of pressure, RC can be much smaller than the Rm, but as the pressure rises, RC becomes the main resistance and which limit the flux. So, typically out of these two, we say this RC is mostly dependent on the delta P. So, we say RC is proportional to delta P, or you can write RC dash delta P. Now, we can write J as Rm plus RC dash delta P. Now, here you just initially this at low value of pressure, you just see the low value of pressure or the cross flow fluid velocity Rm can be much larger than the RC. So, here the Rm is higher than the RC, but as the transmembrane pressure is increasing, you can just see there is a steep rise in the RC value, and RC value accordingly increases. Further, this as this is RC is inversely proportional to the cross flow velocity. So, at low cross flow velocity its value is high, and as cross flow velocity increases, the RC value decreases. Why? You just see Rm is kind of independent of cross flow velocity as well as that of transmembrane pressure. So, this it clearly says that because of concentration polarization, there will be steep resistance, and that is going to regulate the flux. So, next model is the mass transfer model. So, which assumes a simple boundary layer. So, it says you are having a solid membrane and there can be a boundary layer, and you just say thickness of boundary layer is delta. So, it says effect of concentration polarization on membrane filtration is analyzed using mass transfer theory. So, it says the high solute concentration accumulate, in the case of high solute concentration, it accumulates near the membrane or vicinity of membrane separation. So, you can consider there is a Cw concentration at the wall and solute concentration in the bulk Cb. So, for time being you can consider Cb as Cw, and this is the thickness of concentration boundary layer. Now, we have seen Cb and Cw, and when it will pass through it, this Cb, this Cw, and when it will pass through it, this concentration is Cp. Now, we can do this simple mass balance. So, what will happen, this what is coming in is J into C, what is going out is J into Cp, and what is the driving force or what is the rate of accumulation, we are defining using this fixed law of diffusion. So, it says this equals to d into dc upon dy. dc upon dy is the concentration gradient, and d is the solute diffusion coefficient. So, we are applying simple mass transfer theory here. Now, one can quickly rearrange it. So, it says J C minus J Cp equals to d into dc upon dy. So, this will become dc upon C minus Cp equals J upon D into dy. So, one can integrate this. So, what we will get? We will get J as D upon delta. Delta is the boundary condition. It says when y is equal to 0, C is Cb, and when y is equal to delta, C equals to Cw. So, we will be getting C will vary between Cb to Cw depending on the y, and y will vary between 0 to delta. So, we are getting J is D upon delta. So, what is D? D is the diffusion coefficient and delta is the thickness. So, what is the unit of diffusion coefficient is meter square per second, and divided by thickness is the meter. So, we end up with meter per second, that is the same unit of this mass transfer coefficient. So, this can be further written as J equals K ln Cw minus Cp divided by Cb minus Cp. And if the membrane have high rejection coefficient for the solute, then Cp is negligible, and in that case it can be written as K ln Cw upon Cb. Now, using this model, if you try to explain this concentration polarization, so what it says, you have to equation was J as K ln Cw upon Cb. So, it says the Cw is going to change because with time there is a gelation or the deposition is taking place. So, you need to replace the Cw with the Cg. So, then it said K ln Cg upon Cb. Now, it will be able to explain this concentration polarization behavior, because the change in the concentration at the wall. So, it says Cw, this becomes Cg because of the precipitation or deposition of your solute molecule. Now, next comes in the case of membrane operation, there will be fouling. So, the long period of operating causes accumulation of particles, and this fouling we are considering other than the gel polarization. So, these are fouling is caused by, there are foulants, it may be due to quick adsorption of foulants due to change in the surface charge, surface chemistry and structure of membrane. And there is another reason, once this fouling is done, then it slowly decline in the flow rate due to pore plugging or get a layer formation. Further, this fouling cannot be reversed by the changing the pressure, flow rate or the concentration, because it is affecting the membrane property itself. The only way to increase the flow rate through the foul membrane is, now again you have to increase the driving force, or delta P you have to increase if you want to increase the J. So, considering this, there is a fouling factor. So, now we are going to add one more resistance term, that is Rf. Now, it will be J equals to delta P plus Rm membrane resistance, concentration polarization resistance, and then Rf fouling resistance. This is the new term you are adding. So, fouling resistance is not much affected by the change in the flow rate. So, basically it limits how fast the filtration can occur. So, typically this fouling should be avoided, and one option for that is improve the membrane cleaning in order to prevent the membrane fouling. Now, next, that is what are different setup for the membrane filtration. So, there can be modular equipment with different configurations, and these configurations should support the membrane. There should be a membrane. It should allow the high surface area of membrane to be packed in a compact way, means a small volume. It should facilitate the mass transfer between membrane and feed stream, and further it should minimize the risk of particle plugging, clogging as well as fouling. So, considering this, there can be different type of membrane. So, let us say this is the flat membrane. So, they are housed in a plate and frame or castle device. So, you can see the feed streams are entering here, and this is the supporting plate, and these are the membranes. So, what will happen when it is passing through it, it will pass through and permeate will come out over here and feed whatever will not pass through it will be return it. So, this arrangement is housed in a plate and frame or cassettel device. So, and the separation between individual membrane is in the range of 0.5 to 2 millimeter. So, this module, or you can say cartridge, it contains the several membranes and plate unit like a sandwich. In this case, the membrane surface area varies in the range of 300 to 500 meter square per meter cube. So, one disadvantage with this setup is this cleaning of membrane by black flushing is not possible. So, we have to open it and clean it same as the filter press. The next membrane is the spiral membrane. So, it simply is the pair of flat membranes separated and supported by the mesh screen. So, you can see the mesh screen here. So, the membranes are separated by the mesh screen, and their stack assembly is wound around a central perforated tube. So, there is a central perforated tube and they are stacked around it and placed in a tubular outer casing. So, it is a kind of a tubular device, and because of this arrangement it has very high surface area in the range of 600 to 1000 meter square per meter cube, and it operates in a turbulent region. So, the advantage here is the efficient mass transfer with low energy consumption. Further disadvantage is this is easily prone to particle clogging. So, the one option is you have to pre-filter the feed before passing through this filtration assembly, and in addition it is difficult to clean and sterilize for aseptic operations. So, other arrangement is you can have the hollow fiber. So, it contains about 50 to 5000 cells supporting narrow bore membrane tube. Here the difference is that tube diameter is in the range of 0.2 to 2 millimeter, and the membrane thickness is in the range of 0.1 to 0.4 millimeter. So, here feed enters at one end and retenate leaves at the other end. It offers the highest surface area around 1200 meter square per meter cube. Again, in this case pre-filtration is necessary to avoid the filter clogging, but here it has another advantage, that easy cleaning by applying the back pressure to reverse the permeate flow direction. So, if you can reverse the permeate flow direction, you can clean the membrane. So, tubular, this is very much similar to the hollow fiber modules. The only difference is the tube diameters are larger in the range of 3 to 25 millimeter. So, advantage is as this is the larger, so it is less prone to particle clogging, but at the same time it significantly compromises with the surface area. It reduces to 100 meter square per meter cube. In addition, there can be special modules which can incorporate a special design to increase mass transfer at the membrane surface. In some cases, some membranes may spin or vibrate, while other can have arrangement to create turbulence or flow instability by design. So, because of this, it is going to increase the mass transfer coefficient, or you can say it is going to ultimately increase the permeate flux. So, based on the pore size, we can classify these membranes as microfiltration, nanofiltration, ultrafiltration and reverse osmosis. So, here is a quick comparison of microfiltration, ultrafiltration and reverse osmosis. So, microfiltration, it removes the cells and cell debris in the range of 0.2 to 10 micrometer, and typical pore size is 0.05 to 5 micrometer. While if you see in the case of ultrafiltration, the pore size is decreased to 0.001 micrometer to 0.1 micrometer, and if you go further for reverse osmosis, the pore size is in the angstrom, it is 1 to 10 angstrom. So, depending on the pore size, ultrafiltration can remove the colloids, virus and biomolecules like protein, carbohydrate and inclusion bodies, while the reverse osmosis, even it can separate the dissolved salts and the microsolutes from the water. So, for this reason, this reverse osmosis is not recommended in downstream processing for biological product, but it is mostly used for the water purification. And for ultrafiltration, it application overlap with the ultracentrifugation. So, we have to see which one is more feasible for a given process. And microfiltration, its application overlaps with the conventional filtration and centrifugation. So, here you can see as the pore size is higher, so it operates at a low pressure 0.5 to 2 atmosphere, while ultrafiltration it requires high pressure, and reverse osmosis it works at very high pressure. And what is the size? As we have discussed, the pore size here, it is 0.05 to 5 micrometer for microfiltration, or ultrafiltration 0.001 to 0.1 micrometer, and for reverse osmosis it is in the range of 1 to 10 angstrom. And you can just see the examples what they can separate, and based on their applications are decided. Like microfiltration, they are more suitable for the cell removal and clarification. There are different type of cells, but when you go for the ultrafiltration, they are suitable for separation of protein concentration, or even for the virus removal or nucleic acid separation. Further, if you go for the nanofiltration, the nanofiltration is removed for the small molecule separation or even for the partial salt removal. And if you go for the reverse osmosis, it is used for the water purification and solvent recovery, even it can separate the salts. So, you can see depending on the molecular weight also, this molecular weight cutoff is kDa. So, for ultrafiltration it can go up to 1 lakh kDa to 10,000 kDa. It is further decreasing nanofiltration in the range of 1000 kDa, and it is just keep on decreasing, and even it is reaching to the ions in the case of reverse osmosis. So, that is what it indicates. Membrane filtration, it requires the operating pressure as a driving force. So, this may be one operating cost. In addition, the cost of membrane itself is a this major challenge in the case of membrane filtration. Further, as we have seen, there is a concentration polarization as well as the membrane fouling. So, it is very much needed to design this anti-fouling membrane, so that you can increase and improve the life of these membranes. So, with this I will stop here. Thank you so much.